Today we embark on a fascinating journey into the heart of number theory, exploring one of its most elegant and enduring concepts, the Chinese Hermione theorem. This remarkable theorem, first documented by a brilliant 3rd century Chinese mathematician Sun Tzu, provides a powerful and systematic way to solve a particular kind of mathematical puzzle. We are seeking a single integer, let's call it x, that satisfies multiple conditions simultaneously. For our explicit problem, we are looking for a number x that leaves a remainder of 2 when divided by 3, a remainder of 3 when divided by 5, and a remainder of 2 when divided by 7. The core premise of the Chinese Hermione theorem is that such a number exists and it can be found. The foundation required for these theorems to work is that our divisor 3, 5, and 7, in this case, must be what we call pairwise coprime. This simply means that no two of these numbers share any common factor other than 1. Since 3, 5, and 7 are all prime numbers, they naturally satisfy this condition. Our first step is unveiling these mysteries is to establish the overall cycle length of our solution. We achieve this by multiplying all our individual divisor together. 3 times 5 times 7 give us 105. This value 105 become our master modulus, defining the period of our solution. Any solution we discover will be unique only with this cycle of 105 numbers. Next, we calculate what are known as cofactors. For each of our original divisor, we divide our master modulus with 105 by that divisor. So the divisor 3, our first cofactor, is 105 divided by 3, which equals to 35. For the divisor 5, our second cofactor is 105 divided by 5, resulting in 21. And the divisor 7, our third cofactor is 105 divided by 7, giving us 15. These cofactors are quite special. Each one is perfectly divided by all the other original divisors, but not by its one. For instance, 35 is divided by 5 and 7, but not by 3. The pivotal challenge now lies in finding the modular inverse for each of these cofactors. The inverse of its is uniquely multiplied that, when multiplied by its cofactor, leaves a remainder of 1 when divided by the corresponding original divisor. The computational rigor required here is entirely handled by a powerful technique called extended Euclidean algorithm. These algorithms allow us to express the number 1 as a linear combination of 2 other numbers. For our first pair, involve the divisor 3 and the cofactor 35, we use the extended Euclidean algorithm to find that 1 can be expressed by as 12 times 3 plus negative 1 times 35. This tells us that our first modular inverse is negative 1, which is equivalent to 2 when considering modulo 3. Moving to our second pair involve the divisor 5. The cofactor 21. The extended Euclidean algorithm reveals that 1 can be expressed as negative 4 times 5 plus 1 times 21. From this, we deduce that our second modular inverse is 1. Finally, for our third pair with the divisor 7, the cofactor 15, the algorithm shows us that we can be expressed as negative 2 times 7 plus 1 times 15. This provides us our third modular inverse, which is also 1. We can quickly verify this inverse. For example, 35 multiplied by negative 1 is negative 35, which leaves a remainder of 1 when divided by 3. Similarly, 21 divided by 3 leaves a remainder of 1 when divided by 5. And 15 divided by 1 leaves a remainder of 1 when divided by 7. This confirmed inverse provides the essential component for our final synthesis, which all of with our pieces in place, we can now construct the solution. We take the original remainder of each conjugate, multiply it by its corresponding cofactor, and then multiply that result by its modular inverse. We then sum these three products. So we have 2 times 35 times 2 plus 3 times 21 times 1 plus 2 times 15 times 1. Performing this multiplication gives us 140 plus 63 plus 30. Adding these together yield 233. Since our solution repeats every 105 number, we take 233 and find its remainder when divided by 105. This calculation gives us 23. Let's quickly verify our answer. If you divide 23 by 3, we get 7 with remainder of 2. If we divide 23 by 5, we get 4 with remainder of 3. And if you divide 23 by 7, we get 3 with remainder of 2. All three conditions are perfectly satisfied. So 23 is indeed the smallest non-negative integer that solved our puzzle. However, 23 is not the only solution. The general solution encompasses all integers that are congruent to 23 modulo 105. This means any number that can be written as 23 plus any integer multiplied of 105, you also satisfies all three conditions. For instance, if you add 105 to 23, we get 128, which also works. Similarly, subtracting 105 from 23 gives us negative 82, another valid solution. The Chinese remainder theorem is far more than just an anxious mathematical curiosity. Its principles are fundamental to modern cryptography, ensuring the security of our digital communication. It's used in error-correcting code, allow a computer to detect and fix mistakes in data transmission. It even finds application in computer architecture and scheduling problems. This elegant method born from ancient wisdom, continues to be a vital tool in our technology advanced world, demonstrating the timeless power and beauty of mathematics.